Hello everyone and welcome to this 27th lecture in 303 heat transfer. So today we'll talk about internal flows. Till now the discussion in the field of convection was on the external flow. So internal flows are typically flows where the boundary layer, for example, let's say we have a pipe, a circular pipe, then the boundary as soon as the flow enters from the left, it's a uniform flow condition from the left hand side, the boundary layer starts to develop on all sides, and there is a point at which the two boundary layers, the boundary layers are on all sides, they meet. So what happens is, beyond this point the flow then becomes fully developed, but the flow is still constrained. This the boundary layer cannot develop freely, and such flows where the boundary layer is constrained because of the flow happening inside plates or pipes or ducts, these flows are called internal flows. So they're different from external flows in the sense that the heat transfer coefficient is going to be different in these flows. So we'll analyze these flows because they're quite important in engineering applications. Okay, we have to distinguish between the entrance and the fully developed conditions. So there is a point, let's say, let's use a different color. So there is a point from the point of entrance to the point where the boundary layers meet, and this region is called the entrance region. In this region, the flow is still developing, and a part of the flow is in the viscous regime where the boundary layer exists, and a part of the flow is still having a uniform velocity profile from the inlet. Okay, but beyond this point where the boundary layers meet, further to that, on the right hand side, we have a fully developed region where the complete flow is experiencing the viscous regime in the flow. Okay, so of course the heat transfer coefficient also is different in the different regions. So we tend to study hydrodynamically and heat transfer wise. Well, in this case we're talking about hydrodynamics. So we tend to study or discuss these flows as separately, the regime of the entrance region and the fully developed region. Okay. So as I said that the inviscid region of the uniform velocity, it shrinks as the boundary layer grows, and ultimately this shrinks to a size where it becomes zero in the fully developed region. So a question for you is, does the center line velocity change with increasing x? And the answer obviously is yes, because initially when the flow started, it was a completely uniform velocity profile. But since the flow rate is the same, and let us assume that the flow is incompressible, so what happens is that since the velocity now has become parabolic in nature, so if the velocity at the ends has reduced, then it has to increase in the center to ensure that the same flow rate is maintained. Okay, so the answer is yes, the center line velocity has to change and has to increase with increasing x till you reach the fully developed region. Beyond that, the profile remains as it is. So one way to mathematically describe the fully developed region is that your x velocity, which is u, does not change with x. So del u by del x is 0 in the fully developed region. Okay, so in this region. Okay, so as we said, it becomes parabolic in the fully developed region and invariant with x, which is what I've written here. Okay, so a flow can be again laminar or turbulent depending on the Reynolds number. So in this case, we define the Reynolds number based on the pipe diameter. So the RED in this case is defined as the U. In this case, we define we use something called a U mean, which is the average velocity defined based on the flow rate, cross-sectional area. We'll discuss that further. So you can think of, since you had a uniform velocity profile to start with, so it can be considered this velocity, and then you have the diameter of the pipe, which is twice times R naught, and then you have the kinematic viscosity of the fluid flowing inside the pipe. Okay, so if this Reynolds number based on the diameter is less than 2300, we get a laminar flow in the pipe. But if this value is greater than this, then the flow starts transitioning to turbulence, and we have to we cannot assume the velocity profile to be parabolic in this case. Okay, so we are doing a quick recap because you already have learned these things in your fluid mechanics course. So we are just doing a quick recap of those ideas. Okay, so the next is thermal effects. Now let's come to the interesting part, which is of interest in this course. So in the thermal effects again, if you have a flow that is entering the pipe at a uniform temperature condition as shown on the left hand side. So please note that the arrows do not, I mean, temperature is a scalar. So the arrows are simply used to denote the magnitude of the temperature. So as the flow further proceeds, we have a thermal boundary layer that develops as shown by this delta, and this boundary layer grows in size until it reaches this point, beyond which the complete fluid inside the pipe has has seen the effect of the pipe surface. So on the left hand side of it, you can see that in this region, the temperature has been modified because of the pipe surface, the boundary layer, and in the central region, where which is outside the boundary layer, the temperature is still uniform as it was in the entrance region. So beyond this thermal entrance region, that is beyond this point, on the right hand side of it, the temperature profile is completely modified. Now, depending on the boundary condition, it could happen that either you have a condition where the surface heat flux is specified. So in that case, you have this kind of temperature profile, and then you could have a situation where the surface temperature is fixed on the pipe surface. Then you would have a profile which looks slightly different. But again, we'll discuss more about this later, but we just want to get an idea of what sort of temperature profiles we see inside the pipe. Okay, so as I said, that the thermal boundary layer develops on the surface, and then increases as x increases until you reach the fully developed region, which is on the right hand side of this. So we call it a thermally fully developed because we're talking about temperature. So be careful when you talk about the word fully developed, because it may be different for a laminar, and so it may be different for hydrodynamic, that is velocity, and thermal, that is temperature, at least in the laminar flow regime. So a question for you as a food for thought is a temperature profile invariant with X in the fully developed region? Okay. Just as we had in flow velocity, X velocity, that in the hydrodynamic boundary layer, del U by del X, sorry, in the hydrodynamic condition in the fully developed region, del U by del X was 0. Because it's fully developed, so the velocity profile remains parabolic, it does not change. But for the temperature situation, since we have a fully developed region for temperature, can we say that del T by del X is 0? And the answer, if you think about it, is no. Because as let us take a situation where the flow that is entering the pipe, let me erase everything for clarity. If we are taking a situation where the flow that is entering is cold fluid, so as an example, and it is flowing across a pipe which is at a high temperature. So when this cold fluid flows through a pipe, um, it will extract some heat out of the pipe. But as it moves from left to right, its temperature will also increase, and that is what we see in pipes, and that is exactly the reason we have these pipes to exchange energy. So what can we how can we define a fully developed region for temperature? Okay, because what we see here is that del T by del X is not equal to 0 in the fully developed region. It will keep on extracting the energy until the fluid inside the pipe will reach the pipe temperature. Now we are assuming that the pipe temperature is fixed. So Ts, the surface pipe temperature, is fixed. That is the boundary condition available. Then del T by del X will not be 0. So we have we will come back to this question as to how to define a fully developed region, because it the temperature changes with X as we move from left to right. Okay, so before that, let us answer other few questions. For a uniform surface temperature, what may be said about the change in temperature profile with increasing X? Okay, so this is uniform surface temperature. So you have let's say a pipe with T surface equal to constant. So again, the same idea that we've discussed. If a cold fluid is flowing through this, it will start increasing its temperature until the temperature of the fluid reaches surface temperature. So the temperature of the fluid will constantly increase. So if I was to write del T by del X, then it will be a positive value. As the cold fluid moves from left to right, it will increase its temperature. Now, for a uniform surface heat flux, what may be said about the change in the temperature profile with increasing X? So again, if you are constantly providing heat, so if you have a fluid that flows through a pipe, in this case you are constantly supplying a flux. So what is happening is, if you have a fluid that enters the pipe, as it goes in the pipe, it will get hotter and hotter because you are constantly heating it. Okay. So the temperature of, again in this case, del T by del X will be positive because you are constantly providing a temperature flux which is uniform. Another question to address as a food for thought is, how do temperature profiles differ for laminar and turbulent flow? So we talked about laminar, but what happens if the flow is turbulent? So again, as we discussed earlier, that if the flow becomes turbulent, the profiles become much flatter, as you may have seen in your discussion on hydrodynamics and fluid mechanics, that the flow velocity, x velocity, becomes extremely flat, except that towards the ends there is a viscous region. So what happens is that the wall shear stress increases as the flow becomes turbulent. Similarly, what we see is that the temperature profile also is quite flattish. So let's say we have a cold fluid flowing in a hot pipe with a constant temperature condition. So it will be quite flat, and then towards the end we'll see this strong gradient in temperature. So this is our so to say your temperature profile. What that means is that your H value, the heat transfer coefficient, will be high for turbulent region. Okay, so this is again very intuitive. Okay, so the next discussion we will have is about something called a mean velocity. Okay, so if you remember that we defined something called a mean velocity. So what we do is, and again the reason we discuss about mean velocity is because then we'll have to take a parallel with the temperature as an analogy, and then we'll discuss that further. So there is no idea of a u infinity. So u infinity was there in external flows as the free stream velocity, but here what happens is that the velocity changes in the pipe cross section. So we tend to define something called a mean velocity, which is defined in such a way so that the mass flow rate, which is in kgs per second, is defined such that you can find the mass flow rate as the mean velocity times the cross section area times the density. Okay. So although the velocity profile is parabolic, you can approximate that with a mean velocity um, such that um multiplied by rho times AC gives you the mass flow rate. Okay. It is as if the flow was uniform with this velocity giving the same mass flow rate. So so that it ensures the mass balance or the continuity equation. But actually, in reality, the way you calculate m dot is by integrating over the cross section, because the flow is parabolic. So to calculate the mass flow rate, you have to integrate over the cross section, and then you have to. So what you do is you integrate over the area, the cross section area, and you take these. I mean, if you are thinking of this pipe, then you take these strips, which you call dA, on which the u is defined as a function, on which u is fixed, because u is only a function of r. So at a given r value, u will be fixed, and then you integrate over this r, so that it gives you m dot. So if you use these two, this relation and this relation, and you equate them, you get your So this is the definition of So the mean velocity is defined in such a way so that it satisfies this relation. Okay, so this is what you get for your mean velocity. And if I mean, this is true for any cross section, but and any kind of fluid. But if the fluid is incompressible, or the flow is incompressible, and the cross section is circular of radius r naught, then if you substitute those, so you can write your dA c as the 2 pi r times dr. So if you substitute that, and then you can also cancel your rho in the numerator and denominator, and you can write your AC, the overall cross section, as 2 pi sorry, as pi times r naught square. If you substitute these things, then this is the expression for the mean velocity is what you get. Okay, this is what we use to calculate the mean velocity in pipes or ducts. Now we have the same problem for temperature in our internal flows. So temperature, we need a T infinity to define the Newton's law of cooling. But there is nothing like a T infinity in our internal flows, because as we discussed earlier, that as the flow proceeds from left to right, the temperature increases if we are talking about a cold fluid flowing in a hot pipe. So how do we define Newton's law of cooling? At a given x location, let us say I want to define my heat flux, local heat flux, as a function of x. For that, I'll require my T surface minus T infinity. So there's no T infinity. So we need to define some sort of a temperature, which is an equivalent of T infinity in this case. So we use in this case the idea of mean temperature. Okay. So let's underline that. So so we use the idea of mean temperature. So the way we define mean temperature is, so for any given cross section in the pipe, let us say for this cross section, so we'll call this x equals x naught. So at this cross section, there is some fluid flowing in per unit time, and there is, so with that we can associate some sort of energy that is flowing per unit time through that cross section. Okay, so we call it the watts that are flowing through that cross section. And again, you have done this in thermodynamics when you have advection carrying energy, so the flow energy. So that energy we can define using the mass flow rate times the specific heat times the some sort of mean temperature. So this is, so the mean temperature is still not defined, but we are defining a mean temperature in such a way so that the amount of watts that are crossing the cross section, we call it the ET dot. Okay, so that energy, which is in watts, is equal to the mass flow rate times specific heat times some mean temperature. So you can assume it as if you had a fluid of constant temperature cross section across the cross section. So if you had a fluid which where the temperature did not vary as a function of R, in that case you could write m dot Cp times that average temperature, or that constant uniform temperature Tm. But in reality the temperature changes with R, that is with the radius of the pipe. So to calculate that you can use this formula, again very similar to the idea of u mean, the mean velocity we talked about. So for m dot we write a differential element dm dot, so that gives us rho times the velocity times the differential area, and then we multiply that by Cp times T, where T is defined at a particular radius, and then we integrate over the complete cross section, which gives us finally the mean temperature. Okay, so this is how we define the mean temperature in our internal flow discussions. Okay, and again, if we are talking about a circular tube or a circular pipe which has an incompressible flow going through it, and the properties are constant, okay, the Cp is constant. So in that case, my mean temperature simplifies to this relation. Now remember that this u, we also need to know how the u varies along the radius and x. And although we are calculating at a given x, but this is a function of x. So this Tm is also a function of x. So depending on at which location you are, this T mean will be different. Okay. Now, as I said that the reason we did all this is to be able to define Newton's law of cooling. So we define Newton's law of cooling as we find the heat flux, that is in watts per meter square, as H, which is the heat transfer coefficient, and then we have the T surface, which is the plate, the pipe temperature. This is T surface, and then we have the mean temperature. So here, instead of T infinity, as we had in external flows, we have a mean temperature. Okay, so although fluid is not at a mean temperature everywhere above the surface of the pipe, but we remember the H actually comes, the definition of H is taken from the Newton's law of cooling. So we will define H in such a way so that this law of cooling is satisfied. So the watts per meter square that we have on the left hand side is related to the heat transfer coefficient and Ts minus Tm in this way. Okay. Okay. So a question for you is, what is the essential difference between this mean temperature and T infinity? So one major difference is that this T mean is a function of x. Sorry. So this T mean is a function of x, whereas T infinity was a constant. Okay, so T infinity did not change in external flows, but in this case our mean temperature is a function of x. So we have to be careful when doing when doing calculus with this variable, because it is not a constant. So we cannot blindly substitute whatever we had earlier for external flows. We have to do our calculations keeping this in mind. Okay, the next discussion is on entry lengths. So we said that the flow can be split into two parts. One is the initial developing part, and the other is the fully developed part, where the boundary layers meet. So that developing part is called the entry length. I mean the size of the developing part after which the flow becomes fully developed is called the entry length. And since we have different hydrodynamic and different thermal boundary layers, so their lengths or the entry lengths will also be different. Okay, so we define, well, there's a couple of definitions. We already have discussed the RED, which is Reynolds number based on the diameter of the pipe. So for that we use which is the mean velocity across the cross section, and in some cases we won't have a circular cross section, so we use something called hydraulic diameter, which is defined as 4 times the cross section area divided by P. So for a circular case, since the cross section area is pi times r naught squared, we multiply that by a 4, and the perimeter is 2 pi r naught. So this will give us twice r naught. Okay, so for a circular pipe, the hydraulic diameter is equal to the actual diameter. But for other more complicated cross section shapes, we can define the hydraulic diameter. So that lets us calculate the Reynolds number based on the diameter of the pipe. Okay, and since the mean velocity is obtained from the mass flow rate, so you can get this from the mass flow rate, because remember the was defined in such a way that it's the mass flow rate was given as density times the volume, sorry, density times the mean velocity times the cross section area. Okay, so this is how we define the u infinity. So what we can do is we can write u infinity in terms of m dot. So if we do that, so we get this relation for Reynolds number. So just some basic relations, so that we should know all these things for calculations. Okay. And as we discussed earlier, that the onset of turbulence occurs for a critical Reynolds number of 2300, so beyond which the flow starts to transition, and beyond a Reynolds number of 10,000, the flow becomes turbulent, safely turbulent. It may become turbulent between 2300 and 10,000 also, but we are sure that beyond 10,000 the flow definitely is going to be turbulent. And the reason we need to know these things is because in that transition zone between 2300 and 10,000 of Reynolds number, we have to be careful in using the correlations. So we'll see that later. Now the hydrodynamic entry length, which is the hydrodynamic means the velocity boundary layer. So for laminar flows, we see that the size of the developing region is given using this relation, and for turbulent flows, we see that it is the size of the developing region divided by the diameter is somewhere between 10 and 60. Okay. And then similarly for thermal entry lengths, we see that the size of the developing length or the entrance length is given using this relation. We also have a Prandtl number now, but for the turbulent flow situation where the Reynolds number is more than 10,000, the thermal entry length is between 10 and 60. So you can see that this relation and this relation looks very similar, and we have already discussed this, that when the flow becomes turbulent, then the turbulence diffusion, the diffusion associated with turbulence takes prominence over the molecular diffusion of momentum and energy. So the thermal boundary layer, or the thermal entrance length, and the hydrodynamic entrance length, they are I mean the thermal entrance length becomes independent of the Prandtl number. In fact, they both behave the same way, because the macro scale phenomena of turbulence is causing the mixing now. So we already have answered this. Now if you have let's say oil, so gas is typically where the Prandtl number is around 1, it's 0.7, well, that's for air, but for oil the Prandtl number is very large. Okay, so what that means is in this relation that we have here for laminar flows, if our Prandtl number is very large, then the entrance length is going to be very large. So that means the entrance length for energy is going to be very large as compared to the entrance length for momentum. Okay. What we can do is we can assume the flow to be fully developed even in the entrance length region of energy for oils where the Prandtl number is very large. On the other hand, for liquid metals where the Prandtl number is extremely small because the thermal diffusivity is much larger than the molecular diffusivity. So for those situations, our laminar entry length is much smaller. Okay, so this is much smaller than this, the laminar flow entry length. Okay. So that means that we can assume for the entrance region of the hydrodynamic entry length region, we can assume that the temperature is fully developed profile. And again, now the discussion we'll do will be for fully developed conditions, because in the developing region the things are not as stable as for the fully developed conditions. And again, if you are talking about a very long pipe where you are doing the analysis, so the entrance length will be a initial some part, and beyond that the flow will be fully developed. So then it's more useful to understand the fully developed conditions correlations than the entry length, because the entry length region is only a small region in the beginning. So we are assuming here that the flow is steady, that is nothing's changing with time. The properties are constant, and velocity profile etc. are invariant in the fully developed region. So you can assume that your in the fully developed thermal region, the velocity profile is also fully developed. So it is parabolic if the flow is laminar in a circular pipe. Okay. So a question for you. So what can we say about the variation of mean velocity with distance uh, from the tube entrance? Okay. So we already discussed that. So what can we say about del U mean by del X in the fully developed region? Okay, so we know that this is 0, because if del U by del X is 0, then the mean velocity is also not changing with X. Okay. Okay, and the reason I ask you this question is because when we take an analogy with temperature, we will see that this is not the case for the mean temperature. So del Tm by del X will not be 0, because the mean temperature will change with X. Okay, so I will quickly skip through these things. So in pipes, hydrodynamically, you are interested in the pressure drop, because that helps you calculate the amount of the strength of the pump that you'll have to use. So these ideas you already have learned in your fluid mechanics course, how to calculate the friction factor, and from that you can calculate your pressure drop. Okay, and from that you can calculate the power requirement for the pumping power. Okay. But we are more interested in the heat transfer ideas. So as I said earlier that in the fully developed temperature region, it is not true that del T by del X is 0, like you had in hydrodynamics where del U by del X was 0. So then what is it that does not change with X? So what we see is that this quantity, which is uh, the scaled temperature, is does not change with X in the fully developed region. So let's see what we have here is, so we have the temperature, but we have taken the difference in the temperature of the surface of the pipe. So this is the pipe. You have a surface temperature Ts. Now the Ts also may be changing with x. Okay, if you have a constant flux condition, then the temperature of the pipe will change with x. It will increase. Okay. So this Ts minus T, you take a ratio of that, and the ratio of Ts minus T mean. Now this mean also is a function of x. Okay. Let's take a more simpler situation. Let us say my Tx was not a function of x. Okay, for an example, then my Ts was a constant. Then what I am saying is the difference in that surface temperature and the temperature at any point, uh, and I take the ratio of that to the surface temperature and the mean temperature across the cross section, because this mean temperature definitely is a function of x. So this ratio does not change with x. So del by del x of this whole ratio in a fully developed region is 0. Okay, so that is how we define a fully developed region for um, energy or temperature. Okay. So if you were to take snapshots of the temperature profiles, what you would see is that they um, the relative shape of the snapshots is very similar. Okay. They just look like a scaled version of each other, um, and if you calculate this ratio, then this is going to be the same. Okay. Now remember that ultimately the aim is going to be to calculate the rate of heat transfer because that is the aim in heat transfer. So we want to see what happens if there's a liquid flowing or a fluid flowing in this pipe, then what is the amount of heat that is convected from the pipe to that fluid. That is what we want to calculate. So for that we have to calculate the heat transfer coefficient H. And for that we may either calculate H or we may either calculate the Nusselt number, which is defined using which is a non-dimensionalized form of H. So the aim in convection is mostly to find the heat transfer coefficient H, and that is what we have to do in this case as well. So what we can do is, since this ratio Ts minus T upon Ts minus Tm, del by del x of this is 0, so we can actually write, let's call this thing theta, okay, for convenience. So we are saying that del theta by del x is 0. So this gives that theta is a function of, at most it is a function of r. Okay, that's the radius of the radial coordinate. It is not a function of x, because if it was a function of x, then del theta by del r would not have been 0. Okay, and we also know that in this theta we have this Ts minus T upon Ts minus Tm. So if I was to do a del by del r of theta, then since theta, if you see, if you expand the this is theta, then the denominator is not a function of r at all. It is only a function of x. So what this gives you is 1 upon Ts minus Tm. I'm not writing the dependence on x here, but that is implicit. And then you have del by del r of Ts, which is 0 in the numerator, and then you have a minus del T by del r. Okay, so this is what del theta by del r is. And here what we have done is we have calculated del theta by del r at r equal to r naught, which is the surface of the pipe. Okay, the pipe surface is r equal to r naught, not r equal to 0. R equal to 0 is the center of the pipe. Okay, so this is what we get. This is the same as this. And since we know that theta was only a function of r, so del theta by del r is also only a function of r at max. That means it is not a function of x. So this statement on the right hand side means this whole quantity is not a function of x. Okay. Now remember your q double prime using Fourier's law of heat conduction was minus k del T by del R at the surface. Okay. So we can write this quantity in here using q double prime by k, and the denominator stays as it is. And we also know that q double prime using Newton's law of cooling can be written as h times T surface minus Tm. We just wrote that in the few slides ago. So that means we can write this qs double prime we have here. We can replace that by h times Ts minus Tm. So Ts minus Tm cancels, and this gives us h by k. And again, this thing is not a function of x at all. Okay, so what this tells us is that h by k is not a function of x in this pipe. But we are assuming that k is is a constant property. So the heat transfer, I mean the the conduction coefficient, sorry, the thermal conductivity coefficient does not change with x. So that means h is not a function of x. So the whole summary here is your h is not a function of x. Okay, and that is not a very trivial idea, because in the external flows, what we learned was that as the boundary layer develops, the h value becomes smaller. In the we are still talking about laminar region here. Okay, so the h becomes smaller and smaller. Uh, but here that is not the case. H is a constant. Okay, in the fully developed region, of course. So that is something very useful, because we don't have to see the variation of h with x, because it does not change with x. And again, that sort of makes sense, because in this pipe your boundary layers cannot grow beyond a certain limit. Okay, they grow in the beginning, but that is during the entrance region. But as soon as the flow becomes fully developed, uh, the way we define that thermally is that the boundary layers meet. So the boundary layer cannot grow. The size is fixed now. So that means that the temperature profile has also become fixed, or relative profile, of course. So that means that the heat transfer coefficient, or the slopes at the surface, will also not change with x. Okay, an extremely important idea which is plotted here. So that is what you see. So on the on the y-axis you have the heat transfer coefficient, on the x-axis you have the x coordinate. So you can see in the fully developed region that the h is a constant, but in the developing region you see that h actually uh, is changing. And again, that makes sense, because in a pipe the boundary layer starts to grow until you reach the fully developed region. So when the boundary layer is growing, then the ideas we discussed earlier in external flows are valid. So in the beginning the boundary layer is extremely thin, so the h value is very large, and then it drops down as the boundary layer grows. Okay, and then when the boundary layer is has reached a point where it meets with the boundary layer from the other sides, it becomes constant. So now since we have a decent understanding of the heat transfer coefficient, which we just saw that is constant in laminar flows, in fully developed regions, in pipes, we now need to understand how to calculate the mean temperature, because the mean temperature is not known. All we know is the inlet temperature of the fluid that is entering the pipe, and the pipe surface temperature, if that is known, or the heat flux from the pipe, if that is the boundary condition. But how do we calculate the mean temperature so that we can finally calculate the Q, or the rate of energy that is getting convected from the pipe. Determining this mean temperature is essential for the internal flow analysis. So what we do is, like always, we do an energy balance, because whatever energy is leaving the pipe is basically getting convected into the fluid that is flowing, and that energy is then finally that energy is what increases the temperature of the fluid. Again, assuming that the fluid is cold as compared to the pipe. So we do a simple energy balance. So if we look at this control volume, we have, the temperature on the left hand side is mean temperature Tm, and on the right hand side, we since the thickness of this control volume is small, we say that the temperature on the right hand side is Tm plus a differential change in that is dTm. So this small amount of energy that's convected into this fluid in this control volume, through the convection from the surface, is ultimately increasing the temperature of the fluid. So this is in watts. So this is m dot, which is the mass flow rate, times Cp, the specific heat, times the temperature difference it results in. So this energy results in the increase in temperature. So that becomes m dot Cp times dTm. Okay, and this energy, if you want to calculate, you can also write this using this relation, which is Qs double prime, which is the heat flux times the small area through which it is convected in, and that area is the perimeter of the pipe, times dx. Okay, and if you integrate this expression that you have for dq over the complete pipe, then you get this relation for the total amount of heat that convects from the pipe's surface to the fluid. Okay, so you have m dot times Cp times the temperature difference between the outlet temperature, that is T mean outlet. Again, this is the mean outlet temperature we're talking about, and the mean inlet temperature. So we will use these ideas to proceed for the solution of the mean temperature as a function of x. Okay, so this small amount of dq convection is given as q double primes times p dx, which and this is also this q double prime we learned can be written as using the Newton's law of cooling as h times Ts minus Tm times then the p dx. So this helps us formulate a differential equation for Tm. So what we do is we take this expression of um, dq so I'll write it here. So I'm using this relation. So dq convection by dx is this qs double prime times the perimeter, and this dq that you have here, the dq convection, we just wrote that in terms of the mean temperature in the previous slide. So this becomes d by dx, sorry, this dq convection that we in the previous slide we wrote that as m dot Cp times dTm, and then you have a dx here, and this is qs double prime times p. So we can take this m dot Cp on the right hand side. So this gives us this relation. Okay, so we simply combined equation number 1 on the previous slide for dq and the expression for dq in terms of the surface heat flux qs double prime, and then finally we can substitute the Newton's law of cooling expression, and then which gives us the dTm in terms of Tm. So ultimately our equation uh, simply becomes, let's erase this. So the differential equation we have to solve is dTm by d. Remember, it's an ODE because Tm is only a function of x. It's not a function of r because it has been defined in such a way so that we integrate things over r. So perimeter is a constant. It's a constant cross section pipe. H is a constant, and we have Ts minus Tm. Now H is a constant for a fully developed flow. If the flow is not fully developed, then H may not be a constant. So this is the equation. You have Tm, a derivative of Tm on the left hand side, and you have an expression for Tm on the right hand side. So we have seen equations like this, which can very easily be solved by writing Ts minus Tm as another variable, and this gives us some sort of it's very similar to what we get in RC circuits or your chemical kinetics. So this gives us an exponential solution, which we'll discuss later. But a few situations. So for uniform surface heat flux situation, okay, remember that we deal with two kinds of boundary conditions. One is where the heat flux is specified, and the other is where the surface temperature of the pipe is specified. So when the heat flux is specified, that is Qs double prime is a constant, then from this expression that we have here, Qs double prime is a constant, well, P is also a constant, the mass flow rate m dot is a constant, and Cp is a constant. So what we see is that this dt m by dx does not depend on x at all. So it is not a function of x. So that means that dTm by dx is simply a linear profile, because if its derivative is not a function of x, so that means it is a linear profile in x. So this is what we get by solving it. So here's a graph of this. So you can see that your Tm is simply a linear profile throughout. Okay, so there is no assumption of a fully developed region here, and this difference of Ts minus Tm, which is this thing. So if I just clean it a bit, so you have this dTm by dx, and you have this right hand side is P upon m dot Cp h times Ts minus Tm. So if I have to get this Ts minus Tm, then I see that in the fully developed region, since my h is a constant, my Ts profile is also a straight line. Okay, it is also a linear profile because dTm by dx is a constant. It is not a function of x. So that means Ts minus Tm will also be a constant. But for the entrance region, since we have an h here, and that h actually varies with x, so your Ts minus Tm also varies with x. So till this point it varies with x, and then after, I mean, varies in the sense that it is not a linear profile, but in the fully developed region it is a linear profile. So Ts minus Tm becomes a constant. So we already have discussed why the surface temperature vary with x in the figure shown. And finally, to calculate the total amount of heat or the rate of energy that is being delivered by the pipe to the fluid, we simply have to multiply this Qs double prime. Sorry. So we simply have to multiply this Qs double prime by the total um, uh, cross section area, the surface area of the pipe, which is P times the perimeter times the length of the pipe. So the most interesting idea here is this expression. So this will give us the variation of the mean temperature in the pipe without solving for the temperature at each and every point in the pipe. So if we have the mass flow rate known for the pipe, the specific heat of the fluid, the surface heat flux situation. Remember, this is for the situation of uniform surface heat flux, and the perimeter is known, so we can calculate how the mean temperature varies, and then that can be used to calculate the QS double prime at different points in the pipe. So for the other boundary condition, where the surface temperature is specified and is uniform, we can solve the differential equation for that case as well. Again, I won't do it, but when we solve it, we get an exponential variation of the temperature, the mean temperature, of course. Okay, so I'm just quickly browsing through the results. So this is the result for the mean temperature. In this case, we have shown Ts minus Tm upon Ts minus Tm at the inlet. And if I plot it, since the surface temperature is uniform, so we get a uniform straight line here for the surface temperature, and you can see that the mean temperature, it gets closer and closer to the surface temperature. Again, in this case, we have assumed that the fluid is colder, so this delta T, which is Ts minus Tm, it gets smaller and smaller. And if you in this expression that you have here, if you take x tending to infinity, what you will see is that your Ts will approach T mean. That is this temperature, the mean temperature, sorry, the T mean will approach Ts. So this mean temperature will asymptotically um, reach towards the surface temperature, which again makes sense, because if you have a very long pipe and you have a cold fluid inletting the pipe, then since the pipe is very long, so the fluid will ultimately leave the pipe at the same temperature as the pipe temperature. Okay, then we can show the overall conditions. Basically, this delta TO is used for Ts minus T mean at the outlet, and delta Ti is the Ts minus T mean at the inlet, and this can be written as this exponential expression. So we'll be using that a lot for when solving problems to calculate our mean temperature at the outlet. Okay, so this condition can be used. This can be used to calculate T mean outlet. So this is basically the same thing as what we had earlier, but we have substituted x equal to L. So this is for the whole pipe. So that gives us the T mean outlet. So you can see that instead of x we put the L here. Instead of hx bar we have the h bar. Okay. So this can be used to calculate our T mean at the outlet. So this gives us an idea as to if you have let's say for an example you have um, a fluid that is flowing through the pipe, and you are using that hot pipe to heat the fluid. It's some sort of heat exchanger. Then you would want to know when the fluid leaves the pipe, how hot is it, so that as a design engineer you can tweak different parameters, etc., and ensure that the desired heating has been attained. Okay, now remember that we would want to write the Newton's law of cooling expression, and what we did earlier, I mean, if we want to write the Newton's law of cooling expression for the whole pipe, so we would write Q convection as some heat transfer coefficient on an average times the area, that is the so if the fluid is flowing inside a pipe, then that's the pipe surface area That's we call it AS, and then there's a delta T. Okay. Now this delta T for external flows were very straightforward. This was simply the T surface and T infinity minus T infinity. But here, as we said earlier, that there is nothing like a T infinity. So for that we defined T mean. But this T mean, I mean, if we are calculating the Q at a given point in the pipe, let's say at a given X location, then it is okay. We can use T surface minus T mean. But if you are calculating the overall convection coefficient, so this is overall, then what delta T should we use? Because delta T is typically we wrote as T surface minus T main earlier for the local calculation of Q convection. But since our T surface may also be changing if you have a constant heat flux condition, but if you have a constant temperature condition, then your T mean will be changing. So which T mean should I use? Should I use the T mean at the inlet, at the outlet, or what should I use? Okay. So we will want to understand what to do here. So let's discuss that. So the Newton's law of cooling for this pipe for calculation of the overall heat convection. Now remember, this is just a model. So Newton's law of cooling is simply a model which helps us calculate the Q convection or the watts of energy. So what we do here is to develop this expression, I will park it here, right? And I will use this space on the right hand side. So what is Q convection? See, Q convection is the amount of heat that is transferred from the pipe surface to the fluid surface, fluid material flowing in the pipe. So this is Q convection is ultimately resulting in the increase of the temperature of the fluid. So this we can write as m dot times Cp times the T mean outlet minus T mean inlet. So that is ultimately what our Q convection is. And then I can do some algebra here. So I can write this expression in the brackets as T surface minus TMI, and then subtract T surface minus T mean outlet. Okay, so we simply have added and subtracted Ts. So what this does is this gives us m dot Cp, and then we have this Ts minus T mean inlet is our delta T mean inlet, or delta T just delta Ti minus delta T out. So delta Ti means the temperature difference between the surface of the pipe and the mean temperature of the fluid at the inlet of the pipe, and delta T outlet means the temperature between the surface of the pipe at the outlet of the pipe and the mean temperature of the fluid at the outlet of the pipe. Okay. So this is not a model. This is the exact calculation of Q convection. And now this m dot times Cp, we can use the expression from the previous slide. For let's say we are working with constant surface temperature. So for that case, and that is the main interesting thing, because if it's a constant heat flux, then we can simply calculate Q convection as the constant heat flux times the total surface area of the pipe. Okay, so this is for the constant surface temperature of the pipe. So we can replace m dot Cp from the expression that we obtained earlier. I will write it. So this is the logarithm. I did not show that in the slide, but that was an intermediate step when solving the differential equation for a constant surface temperature. Okay, so this is what we had earlier as an intermediate step. So what we can do is we can replace m dot Cp from this in this from this expression. I mean, sorry, we can replace this m dot Cp using the m dot Cp available here. So that ultimately will result in Q convection as h bar, which comes from this expression, and then you have the surface area as times delta T, and then you have well, I'm defining what delta T Lm means. So this actually is delta T Lm, and this delta T Lm, which is called the log mean temperature difference. Okay, so this is how this log mean temperature difference is defined. So basically, we on the right hand side, we started with the Q convection calculation using a simple energy balance, and we obtained this relation, this model. So you can see that this model actually is quite accurate, in the sense that if you can calculate your h bar accurately, this gives you the exact amount of heat transfer between the pipe surface and the fluid that is flowing. Okay, so this is how we get this model for the pipe. So remember this. Remember in the previous chapter also we talked about this LMTD, the log mean temperature difference. So I said that I'll discuss it later. So this is the um, the idea behind using a log mean temperature difference. So it comes from this energy balance. Okay. So again, as a summary, when you are working with a pipe and you would want to calculate the amount of heat transfer or the Q convection overall for the whole pipe, then you use this relation. Okay, so this is h bar, which is the average heat transfer coefficient, times As, the surface area, times the log mean temperature difference. So this log mean temperature difference, it takes care of the temperature changing from the inlet to the outlet, which was not the case for external flows where the T infinity remained the same. But here that is not the case. Okay, so that's the major idea here. So well, this is the same as what we have written on the top.